and welcome to the second lab of Physics 2212, Lines of Charge. So the purpose of this experiment is to learn about charges and their interactions using everyday objects. It is a continuation of the first lab that we did, but with more advanced techniques to be able to compute and model line charges. This lab provides a model of two charge tapes exerting a distributed electric force on each other to determine the amount of charge on each tape necessary to float one above the other. The result from this model was that the magnitude of charge on each tape was 3.882 e to the negative 8th coulombs. This was confirmed by the system being in equilibrium, thus all forces summed to zero, and thus corresponding electric force from the charge tape summed with the gravitational force from the Earth equaled zero. For this experiment, two pieces of clear tape were ripped apart to create charge tapes, one positive and one negative. This was then repeated to create a pair of positive tapes and a pair of negatively charged tapes. One tape of the pair was then hovered in the air by using the electric force of the other tape to oppose the gravitational force of the Earth on the top tape. Because the top tape was in equilibrium, electric force could be computed by first calculating gravitational force. Then electric field and point charge could be computed algebraically to be used as a starting point to compute and model the line charges using Python. So some of the important physics involved are first, Newton's third law. For every action, there is an equal and opposite reaction. The bottom tape and the top tape exert equal and opposite forces on each other. Thus, the magnitudes of their charge are equal. Probably the most important physics principle involved is actually Newton's second law. When a system is in equilibrium, the sum of all the forces acting on the system is zero. So we assume that there are only two forces acting on the top tape, gravitational force by the Earth on the top tape and electric force by the bottom tape on the top tape. So because the system is in equilibrium, then the forces should sum to zero. So thus the gravitational force and electric force will equal zero. We can then determine gravitational force by multiplying the mass of the top tape by Earth's gravitational constant. We then set that to be equal to the magnitude of the electric force. Using the equation for electric force is equal to electric field of the bottom tape acting on the top tape, multiplied by the charge of the top tape, we can then do some manipulation of the equation to have it solve for the charges of the tapes, which, as stated in Newton's third law, should have the same magnitude as they are a reaction pair. In this lab, we'll be using a more advanced equation to calculate the charges as line charges versus point charges, and this equation is listed here. So for my computational model, I took my E-field function previously written in Lab 0 and used it to calculate the electric field of the bottom tape on the top tape for this experiment. This will be visualized using green arrows. I then originally used the point charge I had computed in Lab 1 as a starting point to then compute electric force. I then increased the magnitude of this charge iteratively until the charges corresponding to an electric force that summed with gravitational force to equal zero. Here I have the visualized computational model of the experiment. I created this model by using spheres to represent the sections I had divided the pieces of tape into, 10 red spheres for the top tape and 10 blue spheres for the bottom tape. The green arrows, as said before, represent the electric field of the bottom tape on the top tape. The white arrow represents the electric force of the bottom tape acting on the top tape, and the yellow arrow represents the gravitational force of the Earth acting on the top tape. As you can also see, it printed the magnitudes of both the electric force and gravitational force, which, for the purposes of this experiment, are equal to each other. A few observations that were made were that when comparing the values from the charges of the tape when modeled as a point charge versus a line charge, I found that the line charge calculation was larger than the point charge by approximately 1.5 e to the negative 8th coulombs. The line charge calculation was 3.882 e to the negative 8th coulombs, and the point charge was 2.334 e to the negative 8th coulombs. These estimates differ because they have varying levels of accuracy in their computation. The line charge model is more likely to be closer to the real value because the model more closely represents the actual physical phenomena, while the point charge model is a more generalized representation. Thank you so much for listening to my lab. I hope that you enjoyed it, and if you have any questions, please feel free to pass them along.